Good evening, everybody.
Good evening, sir.
So today we will solve a few problems, okay, from chapter 3. Okay, so regarding the homework, sorry, I could not post it on Moodle yet. I'm still working on it because of lot of the things that I have to do as a part of the dean position, so because of that it is so I could not complete it, but I hope to complete it as soon as possible, so hopefully by tomorrow night. Okay, sorry about that, so we could not do it. Okay, so regarding this uh, the tutorial that we are going to have today, so we will solve a few problems from chapter 3. Okay, chapter 3 is not finished yet. As we talked earlier, we are going to have chapter 3, chapter 4, chapter 5 together in parallel. So we take a problem, we solve, we complete the whole thing rather than going part by part. So but we will be able to solve a few problems from that. Okay, so I also request you to try to solve those problems. If you face any problem, you can talk to me. Yeah, so let's start with 3.1. Okay, so you are solve the problem during the lecture also. If you face any confusion, please do that, so there is no silly questions, but when you ask, that really means that you are interested, and you are following, you are watching those videos closely. So I'm really happy when you ask questions. Okay, so when you ask question, I can also ask a few questions, just to see like how you think that way, but don't be offended because of it. Okay, now the problem 3.1, it says that the problem is given d over dx ae du over dx plus 2x equal to 0. And this is given uh, for this domain. Yeah, and given sigma 1 equal to e du over dx, x equal to 1 equal to 0.1, and then u3 is equal to 0.001. So it is, the problem is given and the question is that you have to find out the weak form of it. And how do you find out the weak form? Very easy. You start with the original problem and you multiply it by w, then you say d over dx ae du over dx plus 2x. Yeah, so dx. Yeah, since x is between 3 and 1, so you are going to integrate from 1 to 3, right? And that has to be equal to 0. Yeah. Then we solve. So in this problem, actually, you see that sigma is given, so that we know that this is a structural problem, but you don't need to write sigma here. You could have just written this, or just du over dx only. So that are also possible to write that way. So this is a mathematical equation that we want to solve using the difference using this fragment analysis method. So now, given this, we integrate it by okay, so we can first expand it. So sorry, not 0, 1, 2, 3, and then we have w d over dx ae du over dx plus 0 to 3 w 2x dx. Okay, and that equal to 0. Okay, or we write integration by parts now. So you get w A, E,
Sir,
yeah,
sir, in that limit will be 1 to 3 in W.
yeah, 1 to 3 only. Sorry. I think I have made my habit to make it from 0 to L, so it should be 1 only. Yeah, whatever the domain is, always should be that only. Okay. So W A E du over dx. Yeah, and you have 3 to 1 minus 1 to 3, and you have A E du over dx dw over dx, right? And then of course you will have the last one, 1 to 3 w times 2x dx will be equal to 0. Yeah, or here we can also apply the boundary condition. So if you see here what it says, u3 equal to 0.001, and e du dx at x equal to 1 is equal to 0.1. So sigma, although in sigma it says sigma, but yeah, sigma does not have a, so it's correct. So this value 0.1 we can put it. Before that you can expand it. Yeah, so we will have wa, right, and then du over dx at x equal to 3 minus WAE du over dx at x equal to 1, right? And then you have the rest thing, 1, 2, 3 AE du over dx, dw over dx, right? Plus rest of it, plus you have this one. So let's write that too, but the next page. So we have 1, 2, 3 w 2x dx is equal to 0. Yeah, so it's coming from this side also. We have something, so we are mentioning that. So looking at it, what do you have here? Here we have WAE du over dx at x equal to 3, and at x equal to 3 we don't have anything here, but we know that what it tells you is, looking at it, if u is given at 3, w has to be 0, so w at 3 has to be equal to 0. Yeah, so accordingly we can put that value. So w at x equal to 3 will be 0, so this will be 0.
Sir,
Yeah.
sir, can we say that as u at 3 is defined as 0.001, so du by dx will be 0?
No, we don't know about it.
Sir, because it is given constant.
No, not like that, man. No.
We
Eh,
will go equation by equation only then, not by values.
no, you cannot do like that. No, see here. No, you are. Let us say you have some values here, like this one, right? So you have 3, like at u equal to 3. Let us say u equal to 3. The value is some value 0.01. Doesn't mean that the slope is 0. Slope will be some whatever the actual slope is, right?
Okay, sir. Yes.
Yeah, got
Yes,
it.
sir. Yes, sir.
So
Yes, sir.
you don't it is not that it's constant there. It is a variable only. I mean, it has a slope, but that you don't know what the slope is.
Okay. Okay, sir.
Okay. So w at 3, then you have ea, and then you have du over dx at x equal to 3. Yeah, and as I said earlier, this is equal to 0. Yeah, so then we have minus w at 1. Yeah, and then ea du over dx at x equal to 1. Yeah, then we have minus 0, 1 to 3, and EA du over dx, dw over dx, right? Then we have plus 1, 2, 3, 2x w dx all equal to 0. Now here w1 is there and E times du over dx at x equal to 1, right? That is given as 0. So some value is given, right? So we have, this is 0.1. Yeah. This we have at 0.1. So we will have that, we'll put 0.1 there. So we will get that. So value E times d over dx 0.1. So we get that really means minus 0.1 we can write. We don't know what is the value of a at 1. So actually a is also a function of x, right? So we can in fact write wa at x equal to 1, right? And then we have minus 1, 2, 3 EA du over dx, dw over dx, right? And then we have plus 1, 2, 3, then 2xw dx, right? So that equal to 0, and of course this is for all w with w3 is equal to 0, yeah? Because we have put that condition anyway, we put like that. So this is what the weak function is. Any question, guys, on this? Any question?
No, sir.
Yeah, okay. Okay. Now, the second question is show the weak form in 3.1 implies a strong form. So that we have done already, same procedure you can use. So we know that the strong form means the weak form, and we also show that weak form implies the strong form. Both are the same thing, so it is up to you. We have done already, so same procedure you can use.
But sir, how do we prove the boundary conditions of the weak form from strong form?
Boundary condition, you know, to begin with, yeah. So I mean, it is just like those boundary conditions. When you start from a strong form, you go to weak form, and in the weak form itself, you have applied those boundary conditions to begin with, right?
Okay, sir. Okay, sir.
Right. So that means boundary condition is actually it's known basically to you. Boundary condition is not something that you have to guess. Boundary condition is something known. Yeah. So only it is just a matter of equation that we are talking about. Yeah. Got it?
So sir, while proving opposite, we'll use these conditions, right?
Yeah. Yes.
Okay, sir.
Yeah. Any other questions?
Sir, I have a question.
Yeah.
Sir, we take w equals 0 at the point where u is defined. U is already defined,
Right.
and non-zero at all the other points where u isn't defined. Sir, what is that physical interpretation of this?
There is no physical interpretation. Here it is just like your weight function is your choice. You can do whatever way you want. And why we do, it is a trick. And what is the trick? Trick is something that we don't know, we remove from the equation. something we don't know. You don't know du over dx at x equal to 3 because u is given here, right? Since either you know u or du over dx, but not the both things. So since u is given here, and in this equation du over dx is appearing, which is unknown. If you put this unknown here, how will you solve it? Yeah, so hence what we do, we play a trick. We choose w such a way that this w is 0 at that point, so we get rid of this term. Simply, that's it. It is just a trick, basically. There is no physical interpretation.
So we are giving weight 0 to that point where u or du by dx is defined.
Sure.
So because we are already knowing this.
Yeah. So that means we are not giving the weightage to the slope at this point. Means we are not giving importance to this guy. You know, we are giving importance to u value. We want u to be the value that is given, but not this one. Got it?
Okay. Thank you.
Yeah. Any other question, guys? Okay. Okay. So here, like whenever we are talking about this weak formulation, so in weak formulation already we do two things. Like we have one thing, this one, which is given us, or we write this w at 3 equal to 0. That means which we have some information basically about the w, how should the w look like. Yeah. Regarding du over dx, we have applied already here. So du over dx information we have as far as the boundary condition is concerned. Now regarding this, where this value is equal to 0, if you see other value like u at u equal to 3, this term we did not utilize it. Yeah, but what happens when we solve it? Then this value has to be somehow like your solution tile function has to somehow has to satisfy this one to begin with, you know. So that means you have to know it, otherwise you will not know the solution. So meaning that what happens is this value you have already integrated in the equation in the weak form, but this value is not. But when you are using any tile function, that time, unless you know this one, you cannot actually find out the tile function. Hence this you have to know. Yeah, so that's what I'm saying. Both are known basically to begin with. Even if it is a weak formulation, both the boundary conditions are known to you. It's given to you. Okay.
So is that, sir, in the FEM we can only solve the boundary value problems? We can only solve. We have to have these boundary conditions.
Yeah. Yes. That's true. Initial value problem you don't solve because that's a different thing. For that you have to do like it is a time integration. Time integration you have to apply finite difference method. That's different method altogether. You got it? Okay. Yeah. So here you cannot use this to solve the initial value problem. That is true. Yeah. Okay. Now problem number 3. If you see consider a trial candidate solution of the form ux equal to alpha naught plus alpha 1. So far everything all right? Any confusion, any questions so far, guys? Okay, if there is no question, this 3.3, if you see, it says a trial candidate solution will be, it is giving at the form of this one. and a weight function of the same form. So Wx is of the same form. So you can say beta naught plus beta 1 x minus 3, which is a weight function. Now obtain a solution to the weak form in problem 3.1. So whatever we worked in 3.1, it is asking you to solve this. Okay, now, so as I said earlier, you have to know to begin with the values. We know at u1 equal to u3. U3 is equal to 0.001. So that's given. Yeah. So accordingly, we have to find out this value to begin with. And how will you do? You put w, no, not w, but u. So u, this one, right? And then we put u, and then we put the value 3 is equal to alpha naught plus alpha 1. 3 minus 3 is equal to alpha naught is equal to 0.001. So you get the alpha naught value to begin with. So we can use this, right? So alpha naught is 0.001 plus alpha 1 this. So basically, we have this equation ux equal to 0.001 plus alpha 1, yeah, and then you have x minus 3. This is the ux, yeah. Then rest we have to work on that. Accordingly, we have wx. The wx we have to find out what will be wx. Wx equal to beta. What is the value of that? Beta 1.
Beta naught plus beta.
Beta naughts. Sorry, beta naught plus beta 1 x minus 3. And what we want? We want w at 1.
3.
Sorry, 3. Yeah, you're right. W at 3 has to be equal to 0, right? So you want beta naught plus beta 1, 3 minus 3 is equal to beta naught. So what do you get? You get beta naught equal to 0 only. So you have Wx as beta 1 x minus 3. So you got the form of this. We have the u and we have w, right? Rest you can do on your own. So rest you can work out. And how will you do it? We have the weak formulation. Weak formulation we can write, which was 1, 2, 3 dw over dx ae du over dx equal to minus 0.1 wa x equal to 1, right? Plus 1, 2, 3 2x w dx. So just rearranged, but it was the same thing. Okay, now of course we are we know that it is valid for all w with w3 is equal to 0, and accordingly we have w formulated. So let's look at the left hand side is equal to 1, 2, 3 and dw over dx. So we can take du over dx first. Du over dx will be equal to alpha 1 simply, right? And similarly dw over dx will be equal to beta 1. So we can write these values. So we have dw over dx. So we write beta 1 multiplied by ae and then du over dx. So it thus becomes alpha 1 dx and is equal to, now other things may be assumed to be constant. So we will assume it to be constant. So we will, because details are not given in your book, so we assume it to be constant. So that becomes alpha beta 1 ae alpha 1, and then you have x 3 to 1, right? So simply,
Sir, we assumed area to be a function of x earlier when we solved 3.1.
yeah, we assumed, but in problem 3.3 the value of A is not given. The expression for A is not given. Yeah, but when we have to solve it, you have to. We cannot just write as a equation and leave it there. So I think that really means by this it means that this is constant.
Okay.
Anyway, we are assuming it to be constant and we are working out. Yeah. Okay, so finally we will get what? We get 2 beta 1 AE alpha 1. Yeah, so this is left hand side. Right hand side is equal to minus 0.1. Then we have W, which is as beta 1 XA and X equal to 1. So simply X equal to 1 we put and we get this value. Yeah, and
Sir,
then
W was x minus 3.
yeah, you are right. X minus 3. That's true. Yeah, I made a mistake. So here x minus 3. Okay, so this is what we have W, and then we have A, right? So we write A here and x equal to 1. Okay, nice. And then we have this term, so plus 1 to 3 2x and W, which is beta 1 x minus 3 dx. Yeah. Okay, now simplification we can do here. So x equal to 1 if you put here, so becomes 1 minus 3, so minus 2. Yeah, so this things becomes minus 2. Rest we can do, so minus 2 multiplied by minus 0.1, so becomes a plus 0.2, so 0.2 beta 1 A. So 0.2 beta 1 A, that's what we will get. 0.2 beta 1 A plus beta 1 will 2 times beta 1 will go out. Yeah, so here plus 2 times beta 1, 1 to 3, we have x minus 3 dx, right? Okay. Is equal to 0.2 A beta 1 plus 2 beta 1, and this we need to integrate. So x square we have, so x square, we make it x cube over 3 minus 3x square over 2. Yeah, 3 to 1. Yeah, is equal to 0.2 A beta 1. Yeah, plus plus 2 beta 1, and here we have 9 minus
27 by 2
okay, so this is 27 by 2
minus 1 by 3 plus 3 by 2.
plus 3 by 2. Okay, so we can have the beta 1, which is common, 0.2 A plus rest is this one. We have to work out the value. Anyway, the answer, you know that.
Minus 10 by 3.
Yeah, you can work out the answer. So I will write like this. Looking at left hand side, so 2 beta 1 A E alpha 1. So 2 beta 1 A E alpha 1, right? And that is equal to this value, right? So I will just write here equal to this, like this. Okay, Okay, so if you compare, you have the beta 1, and beta 1 is again it's arbitrary because W is being expressed in terms of beta 1. So we simply have alpha 1, right? I mean, beta 1, we cancel out, we get alpha 1. We can find out alpha 1 from here. So alpha 1 becomes equal to 1 over 2AE, right? And then you have something like this will be. So you can work out what it comes to be, but you can find out the alpha 1. Yeah, it's any question, guys?
So what are we trying to do here? But we had to prove or
No, we don't. We have to
obtain.
find out like alpha 1, basically the solution.
Okay.
Yeah. So we got the alpha naught already. We got the alpha 1 from here. Yeah. Okay.
And sir, we didn't use the other condition E du by dx. So we have to check that.
No, that condition we have used in the equation itself, right? That's already there. In the weak formulation, it's already there, no? See, we have this equation, right?
Oh, okay. Yes.
This we already there. But this is not as a boundary condition as such. This is as a part of equation itself. So this converts into a constant, basically, which is part of the equation, which is not, we don't enforce. What is the difference here? We enforced you to meet that criteria, meet u at 3 equal to 0.001. We enforced it to begin with, but we did not enforce you to have a slope, the given slope. That means this will may not be satisfied, and we have seen earlier that it will not be satisfied. Yeah, if you can calculate the natural boundary condition, if you can calculate the the one which is given to you, what is given to you? You are given this du over dx x equal to 1 equal to 0.1, but this is the given boundary condition. But based on the the approximate method, E du over dx will be equal to E times, what do you get? E times alpha 1. If you put that value here, you may not get 0.1.
Yes, sir.
Yeah. So this natural boundary condition may not be satisfied, because you have solved some other problem, no? What you are doing is problem itself you are changing, basically, and then the solution of that problem you are finding out. The exact problem of a different problem you are finding out. This is also exact solution, but of that different problem, approximate problem. So instead of changing solution, you are changing the problem itself. That's the thing. Yeah, got it?
Yes, sir.
Similarly, yeah, go ahead.
Suppose as you said that weak form and strong form both are the same, so we can start we can also start it with the strong form, and in that case we will have to have u in some quadratic form, like order of 2. So
First of all, man, when we say both are same, then there is some it is not exactly same. As you know, that solutions we get is different solutions, But what I'm saying is the equivalence depending on like the conditions, meaning that it is possible that the exact solution that you get using the strong form, you can get using the weak formulation as well, provided you select the right kind of trial function. Yeah. So this is not the one-to-one correspondence. It's not like that, because here what you do is we have transformed the problem actually. So actually problem is different. The problem is different, but if the way you transform from one to other, from strong to weak, same way we can also transform from weak to strong as well. So that's what I mean.
Okay. Okay, sir.
Any other doubt, guys? Okay. Now problem 3.4, it says that ux equal to alpha naught plus alpha 1 x minus 3 plus alpha 2 x minus 3 square. Yeah. So it is asking you now use this formulation, and you use this trial function and find out this value. So similar way you can do it, the way we did this, same kind of, only thing is this will require more time basically to solve, so this will be numerically lengthy because you have to integrate and all. Otherwise the same process you have to follow. Okay, so problem 3.5.
Sir, just a second.
Yeah.
Sir, like in question 3.3, it was written, check the natural boundary condition. Is it satisfied? Like you had said that it will not satisfy. So what answer we'll give? Like it can be satisfied if we choose a particular weight function, or like we'll say directly no.
No, it is not satisfied because it is asking about this particular trial function, no, linear trial function. So it is not satisfied for the given trial function.
Okay, sir.
Okay. Now question 3.5, this relates to heat conduction. So we have not studied that heat conduction yet. So we will do this week. Okay, so we will not solve it right now. Heat conduction problem 3.6 also heat conduction problem, 3.7 is torsion problems. All those things you can do yourself, but we will come back to it later. 3.8, it is talking about the continuity and like this. So I think we will study about continuity and this kind of little bit formal we will do later on. So we will not do it today. Now problem 3.9 we will do. Okay. And here it says, consider an elastic bar with a variable distributed spring. So a spring itself be distributed. Yeah. So what is the meaning of distributed spring? Means that we have the elastic bar is there, and this also has a like a with a variable distributed spring, plus a spring thing is also there with that. Yeah? So we have the bar, and then this spring is also there. Okay, so figure 3.11 is given. So actually it is given like that. It is shown something like this. So I don't know whether it will make sense to you, but so we have like this. We have T bar, meaning that this is a force, boundary force or traction we call it. And then this is a body force, which is given as Bx. Then the symbol that they have used for this is something like this.
And stress.
Yeah.
So traction, as you said, is it stress?
Traction is not a stress actually. Traction is force. Yeah, boundary force. You call it traction. We'll come back to it later on. Right now we don't. So this is traction. Formally we call it is equal to boundary forces. Yeah. So this may have, depending on the problem, in 2D problem, it can have unit of force per unit length. Here, this will be just force only. Okay, so it will not. It is not like a pressure. So it has different meaning depending on where you are using it. It can have force distribution also. It can be a total force also. So basically, this T is a, you can assume it as a force. That's it. Yeah, T bar is the force. Okay, this is how it is written. But what is the meaning of that is the more you go, like apart from this one, it has some variable spring attached. Yeah, I mean that really means, I tell you what that really means. So what we will do here is we will take a slice and you are going to formulate it. So which all things you get? You will have bx, right? Then you have, as we did earlier, we have sigma x, then you have sigma x plus d sigma over dx term here. Yeah, that's how we will do. And then we also have the this px. The px is the spring, distributed spring, it is saying, right? So distributed spring. Distributed spring means what? Force will depend on u basically. So if ux is the if ux is the displacement here, then the force which will be acting in this direction will be equal to px times dx times u. That's what its meaning is. Yeah. Px is like a spring constant, but it is distributed. It's given as a per unit length. So you have to multiply it by dx, and multiplied by u means px times dx is the spring constant, multiplied by u is the force, right? Okay, so what we will get here is, if you look at this one, we get, of course, we will have like area also. So if we have the area here, some A, so we can write it as sigma d sigma over, okay, so sigma plus d sigma over dx times A, right? And then minus, right? Minus sigma times A. So in fact, you can also have the area which is increasing. So in fact, you can also write like in terms of not only sigma, but you can write it sigma times A x multiplied. So you can also have sigma times ax here, and here also sigma A right there. So you can also have write like that. Yeah. So if we have like that, so that we will also have A as a increasing, A as a function of x. So we get in x direction, all the forces has to be equal to 0. So what we get? This A times sigma x. So we get sigma A plus d over dx, sigma A times dx minus sigma A. So that becomes this minus this, right? And then we will have minus
px
px dx times ux. So we got this value. Yeah. Okay. Now what? We have bx thing. So which is in x direction. So plus bx, which is distributed force. So bx times dx we will write. Yeah, and that is equal to 0. So or this will cancel out. So we will get simply d over dx sigma A dx minus px ux times dx plus bx times dx equal to 0, or d over dx sigma A minus px dux plus bx equal to 0. So this is what your equation. Yeah. Any question, guys? So this is what the strong formulation will be, and you know that sigma is equal to E du over dx. So you can write accordingly. So final form will be d over dx Ea du over dx. Yeah. Then minus px ux plus bx equal to 0. And the question says also you find out the weak formulation of that. So you can accordingly, we can do the weak formulation. Yeah. And how will you do it? So let's do it. So weak formulation. So we are going to multiply it by W and integrate from 0 to L. Yeah. So 0 to L W d over dx Ea du over dx minus px ux plus bx, right? Dx is equal to 0, or we can expand W d dx Ea du over dx minus 0 to L W px ux dx and plus 0 to L wx bx equal to 0, dx equal to 0. Yeah. And since the problem has like this, we have the problem says what? This is fixed here, and here you have a t bar which is given. Yeah. So your boundary condition is what? Your boundary condition is u at x equal to 0 is a boundary condition, and here at x equal to L you have t bar. So you will have sigma times A, or Ea du over dx at x equal to L equal to t bar, right? So these are the boundary conditions, and those things you have to put it here, right? So you know that if you work on this one, this will simply look like this: W Ea du over dx, and then you will have L to 0 minus 0 to L Ea du over dx dw over dx, right? minus you have this term, right? So we have W, you can just write here W, then you have Px Ux, right? Dx minus W
Sir,
Px
in
Ux
this,
dx. Yeah.
what, sir, in this, what we are considering as u or v, because e and a are also functions of x.
Yeah, all of them function of x. Only thing I'm not writing here. Yeah, so E and A are all function of x only.
So, sir, which in doing integration by parts, which we are considering as u and which we are considering as v?
Okay, that you are saying. Okay, so here, see, this is already inside it, no? So you can write like this. See, the same thing we can write. So let me explain here itself. So you have like this one, right? So how can we write? We can just write like this, 0 to L, and let's say
The first function is w, and we have integrated the ea d over dx completely.
right. So how do you, so let's not write the limits if you have just integration, and we have we write d w dv is equal to, what do we do? Will be equal to wv minus integration v dw, right? That's what you do, right?
Yes, sir.
You agree? Now here you say, what is the trick? You have dx here, you have dx here, cancel them out. You will have w d ea du over dx, that's it, right? So this multiplied by this is this one. So this is your v. So this is your v, right? Why? Because this cancels out, this and this will cancel out. So you have dv, right? So w dv is equal to w times v minus this times dw, right? But when you say divided by dx, automatically divides by dx and multiplied by dx. So that's why dw over dx terms comes. You got it?
Yes, sir. Yes, sir.
Okay. Okay, so you got this as well, and then you will have plus, of course, 0 to L. So 0 to L, then bx dx is equal to 0. You have w term as well. So you see, we have done that. Now this one, this kind of problem is a complicated problem, you know. So what is the complication here? Tell me. What is the meaning of that? If you have this, then what happens? We can.
Sir, we need something by px. We need some values of px, some function at least.
No, you will get that. But tell me, what kind of complication this brings?
So we cannot find any value for w also.
No, it's not like that. Okay, I will tell you. So let us rearrange it. So we can write here we have we at x equal L, and this we know that EA this is equal to T bar, right? So we can write this equation becomes W at L times T bar minus, now U at x equal to 0, so it will be 0 because W 0 will be 0, so we have this, then minus whatever the value we have here, right? So we can write like this plus write like this, 0 to L W bx dx is equal to, so this and this we are combining, equal to, we are writing this and this. So what do we get? You get 0 to L EA du over dx dw over dx plus 0 to L w p u dx, right? You will have w also p. Okay, now when you work out this, you see here you have u, you have w, here also you have u and you have w, but this side you have just w and w. When you put the expression for w and u, you will find this side you will have both alpha and beta both. Let us say you are taking linear, u equal to alpha x and w equal to beta x. This side you will end up with alpha beta both. This side you will just have beta and beta only. So beta cancels out. What you remains is beta this, alpha this side, right? What happens is basically, what I mean to say is this will end up with equation. If you write, maybe you will understand later on. So this becomes x equal to ku type of form. What it means is this will contribute to the stiffness matrix. We will study later on, but I'm giving you the heads up right now only. So this is a kind of, this turns up into k times u. This is nothing but k times u you will find. And this is nothing but f. So this k times u, and this also has k times u. So this expression also ends up, gives some contributes to the stiffness, and it should do. Positively it should do, because you have this distributed spring. So of course the stiffness has to provide the stiffness, and hence you have that. You got it? You got it, guys? Subhanath, did you get it?
Yes, sir. This is clear, sir.
Yeah, okay. Others, you got this?
Sir, got the question, but not f equals to ku part.
Okay. So because we have not got into how to convert into k, so k thing we have not yet actually got into. You will see that. Okay. Finally, remember that whatever we are doing, our efforts is to convert from a differential equation to a linear equations or the system of equations. Basically, from differential equation, we are converting it to linear algebra, and then we solve it. Why linear algebra? Because it's easy to solve using computers. Yeah. And then we do it. Right now, whatever we are doing it, we are finding out the coefficient. Okay, we are finding out the coefficient. We assume the trial function and find the coefficient, but we will formulate, or we can assume a trial function such a way that we will get in this form, and that we will do later on. Okay, so maybe the next week we will do. So we will come back that time and here. But right now you can assume that K is a matrix, U is the one which has the alpha, right? The coefficient, and F is the one which is a constant terms. So then we invert this one and you can find out the alpha matrix, alpha vectors, right? Alpha 1, alpha 2, alpha 3, right? So to this matrix, this also contributes. So this is a kind of, why it contributes? Because this contributes to the stiffness, and this concept we will know very soon. Okay, I'm giving you a heads up right now, but we will study this. Yeah. Any question, guys? Okay. If there is no question, okay, see you guys tomorrow. Okay, so this week we will work on other kind of problem, or we can also, the concept we are thinking about, we can also talk about the different kind of test functions and how the finite element method is different from the Greikin method or the Rees method. Okay, so that we will look at, and then we will see some different meaning, then we can make connection with the chapter 2. Okay, so far we are not making connection with chapter 2 because chapter 2 we had this f equal to ku, but where is kf equal to ku? So we will make connection. So this week we will do. If not, then next week certainly. Okay, guys. See you tomorrow.
Sir, just a second.
Yeah.
Sir, in the program that you had made us do, like you had written, like you had defined degree of freedom of element like 5, 7, 8, because they were the free degree of freedom or free degree of freedoms. After that, you had done K DOFE, comma DOFE. So can you please decode that part, because I'm not able to analyze what it signifies, what it is doing.
After that, what did I do? Say again.
K of in brackets, like you were trying to fix the degree of freedom, which degree of freedom we want to assign.
Okay.
Like I understood what you were trying to do, but I was not able to understand DOFE, comma DOFE, how it is telling which element it is.
Okay. So programming part you are saying, right?
Yes, sir.
Yeah. So K could be a matrix, right? So let's say matrix is like this. We have 1, 2, 3, 4. 1, 2, 3, 4. Yeah, and you have like this. You have entries here, right? So you will have value K11, K12, and so on, right? You will have like that. So let us say you want to choose here K22, K24, K42, K44. You want to choose this. Then how will you write? In MATLAB, you just write K and you give here 24, comma 24. Yeah, so it automatically give you this value. And instead of writing 24, I will use DOF. So
yes,
DOF, yeah, DOF equal to 24. So actually we are writing K DOF, comma DOF. Just programming trick. Yeah, got it?
Okay, sir.
Yeah, Sugnath.
Sir, actually, I am asking that last class you told about some assignments. So where did I find the assignments?
Man, I have not been able to finish it. Okay, so I will do by tomorrow. Most likely. So I don't want to actually promise, given the lot of things because of my, other position, the dean position. Because of that, I lot of meetings and many things go on. So, but I will try. Definitely by tomorrow night, you should get it. So I'm still working on it. What happens is in this online mode, so I have to put a lot of efforts, so otherwise otherwise in offline mode it's very easy, but in online mode putting on Moodle requires a lot of work. I also want to make such a way that everybody works, it cannot be copied and all. So this is for your own good. This is for good students because they put a lot of efforts, and if they put efforts, it should be reflected in their grade as well. So because of that, I have to do. So definitely, or I will say most likely by tomorrow. Okay, so I will post the message on the Google Classroom accordingly. Okay.
Okay, sir. Okay, sir. So handwritten will be given. We have to
No. So you will know. Just wait. Okay. You will know.
Sir.
So on Moodle, you have to log in and you have to click, and the questions will come, and you have to solve the problems and write the answer, numerical answers there.
Okay. Thank you, sir.
That's what you have to do. Okay. Any other question, guys? Okay. If there is no question, see you guys tomorrow. Okay. Good night, guys.
Thank you, sir.
Thank you, sir.